All right, I guess we'll start then. Welcome to our Zero Knowledge workshop, and we're really happy that you guys made it in person. Again, this session will be recorded for all of you guys who's watching online or sometime later. This, again, is a session that welcomes everyone to the concept of zero knowledge, but it's not really like a super deep technical dive of it. We hope that by providing this workshop to you guys will be able to be able to know what to look for when you guys are doing your own research. This really just provides like a fundamental basis for what zero knowledge really is. And we hope that you guys, after listening to our workshop, you guys will be able to explore more of zero knowledge on your own. So welcome. Let's get to the first question. How do we normally prove a statement? Let's say in math or science, when we have a statement, how do we normally prove it? Let's say in an example where we're in a math class, right? There's an example prompt. How do we know what the value is? We do some work, we give an example, and we provide some evidence to, let's say, a plus b equals to c. And it's through by providing the evidence of some other equations, we can prove that a plus b equals to c. The same way, another example for proving a statement that you're over 21 in a bar is to provide your ID to the club bouncer. They look at your ID, they see, okay, this person may or may not be born like in 1980s. He definitely does not look like he was born in 1980s. He's very young, but I'm just gonna let it slide because he put $20 beneath the ID card. But on the ID card, it shows your date of birth, a lot of other personal information, which provides an evidence that you're over 21. The last example we're gonna be looking at is, let's say you're logging onto a website. We all have Google accounts. I think most of us do. It's really kind of sad we don't these days. How do you provide your password to your account, and if your password matches, then Google knows that you're the right person. Again, you're providing the secret, sensitive information of your password directly through the internet, which might get hijacked, depends on what SSL encryption the website is using. So this is normally how we prove a statement. But imagine if there's a way we can prove the statement without revealing any other information other than the fact that this statement is true. This is where zero knowledge comes in. Well, before we dive into zero knowledge, let's discuss some of the problems with using a traditional non-zero knowledge proof. It's quite obvious your personal information might get exposed to the public. If you're providing your ID card to a club bouncer, that person may or may not just like copy down your ID, use it on some other shady websites, and get you in jail. That's a possibility. And if you're trading publicly on, let's say, Bitcoin, there's all of your transactions are transparent because there is no zero knowledge proof in the system. I can see exactly how much balance there is in your Bitcoin wallet account. And without zero knowledge proof, we might also need to do like a lot of unnecessary work. Let's say you're, again, going back to the example of your math class. You have to maybe take like 20 questions in your math exam to prove that you have a fundamental knowledge in, let's say, calculus. But this is maybe not necessary by using zero knowledge proof. If you can somehow generate a proof that proves that I know 100% of what's being taught in this calculus class without doing any of the physical problem, that's a much quicker proof than you doing, let's say, 20 questions in a math quiz. So how does zero knowledge really work? Let's examine the system of a zero knowledge proof. So in a system of zero knowledge proof, we have two stakeholders. One's the prover and one's the verifier. The prover is the person who's trying to prove to the verifier that a statement is true. And the verifier basically will be listening to the prover and evaluating the proof generated by the prover and evaluate on whether or not this person believes the statement is true or not. There are three fundamental criteria for a zero knowledge protocol. One is completeness. If the statement is indeed true, then with high probability, the prover can effectively and objectively convince the verifier that the statement is true. So let's say if the outside the weather is clear, then I can, with high probability, prove to the verifier that outside the weather is clear. The next criteria is soundness. If a malicious prover cannot convince the verifier of a false statement, even if he tampered with all the other information, with high probability again. So let's say if the weather outside is indeed not clear, but I'm trying to prove that the weather outside is clear, with high probability, I will not be able to do that to the verifier, and the verifier will decide on the fact that my statement is false. And the last statement, the last criteria is zero knowledge. So no other information is being transmitted or exposed other than the statement itself. I'm not revealing any other information about my personal details or maybe like what day it is today, what time is it today, other than the fact that outside the weather is clear. Yeah. So I hope that we've all played with this book called Where's Waldo in our childhood. So it's very straightforward. We have this right here, this dude called Waldo, and we're trying to find him in a crowd, right? I can prove to you that I know where Waldo is without revealing where Waldo is. This is an example where zero knowledge proof. And again, we designed this canvas specifically such that the width and height of this photo right here is smaller than half of the entire slide's width and height. Therefore, we can move this picture around to all four corners without revealing where this photo is if we were to show where Waldo is. Well, here I'm going to prove a statement. I know where Waldo is. How can I prove that? Well, I can just show you where it is right here. Might be a bit dark, but here's Waldo's face with his iconic glasses. But you can see that this is Waldo, but you have no clue whether or not Waldo is in this position of the frame or this position of the frame. This is a very straightforward example of zero knowledge proof. So far, does any of you guys have any questions about just how zero knowledge proof, the concept of zero knowledge proof? All right, cool. So back to the idea of how zero knowledge proof can be applied in Web3. I mean, we are the Web3 builders, and we are researching, and we're interested in seeing how technology can actually be applied to create value in the blockchain zone. So some applications of zero knowledge proof in Web3 is it can create, it's a very fundamental crucial components to creating like a zero trust environment. Such example is that I can outsource intensive computational tasks to other malicious nodes without having to rely on them like correctly calculating my the result of my computation. If I can just ask him to produce a zero knowledge proof saying that all of the calculation is correct without me having to repeat to do the calculation myself. Some other thing are general data privacy, right? The example I talked about before was Bitcoin, where everything is transparent. No longer needs to be transparent if we use zero knowledge proof. Imagine we can send and receive like tokens on a public permissionless network, but none of the transaction will be revealed because everything will be calculated using zero knowledge proof. So there's no like plain text transaction between Alice and Bob, but there is like a zero knowledge proof proving Alice and Bob's value without revealing what that value actually is, other than the fact that Alice and Bob knows exactly how much the value is. And another very interesting, I guess, use case of zero knowledge proof in blockchain is rollups, especially ZK rollups, zero knowledge proof rollups. So in a case with blockchain, as Vitalik once said, he believes that there is a trilemma in blockchain, such that decentralization, scalability, and security, all three factors cannot be achieved at the same time. But however, he made that statement before zero knowledge proof was widely accepted and widely researched. So with zero knowledge proof, we can actually improve on all three aspects of the blockchain trilemma.
What's a rollup?
So I'm moving on. So rollup is how we can basically we bundle up a bunch of transactions together and we verify that all these transactions are correct without having to individually verify each of the transactions is correct. Yeah.
How is that different from the hashing thing we explained earlier?
Would you elaborate which hash we were?
No, like in hashing, we were like, oh, we bundle up so many transactions together, and the hash basically contains like the whole history of those transactions, but like all those blocks bundled together. So like what you're describing as rollup sounds kind of similar. So like, what do you say the difference is?
Well, that's just to what you're describing is a different use case. Hash is basically proving the integrity of two different copies of data, while here we're proving that each individual record within the transaction, within like the rollup, is indeed correct and verified. Yeah. Yes.
What's the difference between outsourcing computation and scaling with ZK rollups?
So outsourcing is just like it's another different use cases. Let's say if we have like an EVM, like a virtual machine system, and you want to outsource some work. You can bundle up that work in a zero knowledge proof system and let the executor of that job produce a zero knowledge proof stuff. And at the end, you verify that the proof that this person provided is indeed what you expected, without you having to actually to do the work. This end rollup is not related at all.
That's how ZK roll.
No.
So ZK rollup is specifically you're taking originally blockchain work, but now you're having an offline computer to execute it. But outsourcing computation can be anything, right? Like I can do like I can compute some data analysis, and then I'm asking someone else to do it, and then I use ZK proof, have them to prove to me that they did everything correctly. So it could be way beyond blockchain.
Yeah. But again, people are looking into building like computational networks with blockchain, and yeah, so yeah, like outsourcing computation can be application in the blockchain setting. Yeah, so these are just some of the examples with ZKP and Web3. There's a lot more other examples that ZKP can be applied to. We're very excited to be diving deeper into how exactly can we do these things. So yeah, how the hell does ZKP really work? This all sounds very magical, but how does it work mathematically? We have in math the discrete log problem. If you guys are not familiar with that, there are some mathematical problems that are very easy to solve in one direction, but not the other. If you look at the example of mixing paint, you can see that this is playing reverse, by the way. You can see that we start with blue and yellow paints, and it's very easy for us to see if they mix together, we'll get this kind of greenish color. But if we just give them the greenish color, it's really going to be very hard for us to see like what color was like that into which is blue and yellow at this point, unless you have the time of unless you have the ability to time travel. And some mathematical problems are just like this. One of it is modular arithmetics with the discrete log problem. So it is very easy to calculate the value of a to the power of b mod c, but it's very hard to calculate the value of b given the value of a to the power of b mod c, if the modulo is sufficiently large enough. So for those of you who don't know what a modulo is basically if you divide something and what you get for the remainder of something. Imagine that we have a clock right here, right? Let's say we have a value from 0 to 5, so that's 6 spots. And we have a value, we have a string with a length of let's say 8, as illustrated right here. We wrap the string around the clock over and over again until the row ends, as you see it's right here too. So that is the value of 8 mod 6. Yeah, and the order of the modular operation is not important. So with the example of 3 times 4 minus 1 times 3, this entire thing mod 6, we know the value is 3. Just simply plug into your calculator. But the fact that 3 times 4 mod 6 minus 1 mod 6 times 3 mod 6 still results in 3 is a very interesting mathematical property. If you want to dive deeper into like how exactly does this work, you can Google it. We're not going to be covering it in this session. So with that property right here, we can extend this to something more interesting: homomorphic encryption using discrete log. So let's say we have a value a in which that we want to encrypt, and so what we want to do first is choose a generator number. So as we define right here, a generator number is a very, very special integer number, such that for every a in a z prime, we have g to the power of k equals a for some integer a. So what that means is that basically, if for this generator number, that number to the power of something will effectively span across the entire domain of the number space. So now that we've chosen a generator number, a very good generator number is either 3 or 6, but there are a lot of other generator numbers. We can encrypt the value by having the equation of E of A, which is the encryption of A equals to G to the power of A mod N. That will give us like the modulo that we talked about before. And we can actually do additions and multiplications without even knowing what A ever is, by simply applying the algebraic property of we multiplying two numbers with the same base, which G to the power of A times G to the power of B mod N equals to G to the power of A plus B mod N. Since the order modulo does not matter, as I explained before. Yeah, and the same thing can be applied to multiplication. You just have to basically put G to the power of A and then to the power of B. That will give you G to the power of A times B mod N. Any questions about the math here? All right, let's proceed. So, okay, now that we have all these information ready, we can actually do something cool. Let's say we have a statement that the prover knows that there exists a polynomial p of x, and he knows that a and b are the roots of this polynomial p of x. This is public information. And the prover wants to prove to the verifier that I know the remaining roots to this polynomial. So how can I prove, like, what does it really mean that I know the remaining roots to a polynomial question? So any polynomial with roots a and b can be represented of p of x equals to h of x times t of x, where t of x equals to x minus a times x minus b. Those are just the two roots, where the h of x, is what the remaining roots are. I hope you guys learned this back in like high school or something about how polynomial works. And okay, so the prover wants to prove to the verifier that I know what this h of x is without revealing what this h of x really is. So the prover is only proving the fact that like I know what this h of x is. And how can the prover do so? We have this protocol written right here. So at the beginning, verifier wants to choose a random value of x, which is going to be just a random sample on the polynomial curve. It can either be 3 or 300. It really doesn't matter. It's just a random sample. And the verifier wants to calculate the encryptions of all of x for the power of like from 0 to the degree of the polynomial d. And you can do that by e of x to the power of I, where I equals to 0 all the way to d, where d is an integer. And then you want to evaluate these the unencrypted target polynomial, which is going to be the value of the polynomial that the prover is trying to calculate. And then the verifier passes in all passes all the encrypted powers of x to the the verifier passes all the encrypted value of x to the prover. So all the prover has is a collection of encrypted x to the power of 0, x to the power of 1, x to the power of 2, which are effectively part of the equation, right? So for the prover, the prover knows the constant c to the power of 0, c0, c1, c2, all the way to cd, but prover is trying to prove what these weights are to the verifier without revealing what they are. So now that the prover has these information, he can actually just apply the math of what we talked about before by actually multiplying and to the power of c1, c2, all the way to cd to calculate the remaining h of x of the polynomial. In this entire progress, in this entire like proof system, not a single time that the actual value of the polynomial is exposed, not a single time that the value of x is exposed, but after doing the calculation and providing the sum, prover passes that back and the verifier can verify that this value is indeed g to the power of something something, which is that something something is t of s times h. And now that we completed this progress of verifying the polynomial without ever revealing what x is and the remaining part of the polynomial. Yeah.
Are there other protocols? Like how many are there? Like generally?
There is a lot. This is actually what we could find this most straightforward protocol. But Intel will be talking about a lot about like what other applications there are, in which a lot of smart people gather together and generalize this into something called ZK stars. And yes.
I mean, I don't really understand the math, but there's no way for them to like backtrack it back to like the secret number or whatever.
No, not really, because if we look at this again links back to modular it's this very property that it's very easy to calculate a to the power b mod c, but it's really hard to go the other way around. And that is what determines the hardness of this problem. We're basically working with some very hard problems in math. And if you study like NP completeness in maybe 6262, you'll get a better grasp of it. Yeah. So transitioning to a more generalized situation with ZK stars.
All right, cool. It's my turn now. So Brendan went over discrete log because it's a really easy example to begin with, but that is not what actually being used, what's getting used in the field. We need to look at more general problems, and we're using the same intuition about cryptography as Brendan suggested, the discrete log problem. That's a sort of trapdoor problem where it's easy to compute one way, but if you want to back the other way, it's very difficult. So we're going to use a different kind of cryptography, but sort of almost the same idea. And we're also going to take on new challenges, right? So what Brendan just said is sort of, there's one secret number and you're just sort of manipulating and proving computation on top of it. But how do we go from here to proving the correctness of executions? How do we go from here to proving, you have a series of code, you have thousands of lines of code, prove the correctness of execution like that. So we're going to use something called ZK snark, or we use the general structure of ZK snark to give you guys a bit more intuition about the math behind how everything works, so that the next time you see zero knowledge, it's not this magical black box, but instead you have sort of, you're taking a little peek into how it works. Of course, at the bottom, you see that, there are many leading, or not leading, but prominent or infamous companies who are working on using zero knowledge to solve many challenging problems. Alio is doing sort of privacy app development platform. Tornado Cash, infamous in the sense that they're banned in the US because they mix money for terrorists or freedom fighters, depends on the way you see it. And then there's also ZK Sync, which is the problem that Brendan mentioned to scale the EVM, because currently most of the general purpose blockchains are relatively slow. And ZK Snark stands for Zero Knowledge Succinct Non-Interactive Argument of Knowledge. For us, we're going to mostly focus on the argument of knowledge, which is like proving something that's in a zero knowledge way. It also has the attribute of succinct and non-interactive. I would say those are interesting, but they wouldn't be the emphasis of this workshop. So the roadmap is that we're trying to solve prove the correctness of this very simple math expression. Is like we have input x, we want to compute x plus x cubed plus 5 and guarantee the correctness of the computation in a zero knowledge way. To convert that into code, on top you see this is like a Python syntax almost. Def eval q eval of x takes in y is x raised to the third, and you return the x plus y plus 5. So how we're going to do this is that first we have this argument or statement, and then we're going to turn it into expressions, and then we turn it into polynomials, and then we encrypt it, and finally we have a proof. And you'll see that sort of the polynomial and encryption steps is already very similar to what Brendan talked about in discrete log, sort of on a high level, but the cryptography is a bit different. So first we turn the argument into expressions. So we have this code, and then now we turn it, we convert it into a form where we have almost like z equals x operator y, where in this case we only have multiplication and addition. So, and also because we can't use things like raised to the power of, so we have to break up some procedure into 2 steps. So on the first line, you see that symbol 1 is intermediate result equals x times each other, so x squared. And then you have y equals symbol 1 times x. Now you have y equals x raised to the third. And then symbol 2, another intermediate result, which is x, y plus x. Eventually, you have this intermediate result plus the constant of 5, and that's the output that we're seeing here. So this is the equivalent, except now you're putting it in a new form. So you see that now we have 4 lines of these sort of expressions. Next, we're converting these expressions into something called R1CS, rank 1 constraint system. So the 4 lines that we saw before now becomes 4 constraints. And in particular, we are encoding them in this format of s.a times s.b minus s.c, where s is sort of the answer, the vector assignment at the bottom, including all the original inputs, output, and as well as the intermediate like results. So you see there's like the 1x out, symbol 1, y, symbol 2. And so there's actually a one-to-one mapping. So you see that, so let's look at the first line of A, B, and C matrix. The first line of A is 0, 1, everything else is 0. So the 1 is in the second position, which corresponds to X. And then the first line of B is also 1, which corresponds to X. And then the first line of C is the fourth, which corresponds to symbol 1. And that is exactly the first line of the code. So that's how sort of these map to each other. And you can also see that, in this matrix representation, the number column is number of intermediate parameters, and number of rows is number of flattened expressions or constraints. So you can actually see sort of, how you can dot product this together. If you pass in a valid assignment of 1, 3, 35, 9, 27, 30, which essentially is setting X to 3. So X to 3, you have X squared equals 9, X third 27, and then plus other numbers. So if you feed in this vector assignment into A, B, and C, and the result would actually come out to be 35 times 1 minus 35 equals 0, which means that, or how this works is that if you feed in a valid vector assignment of, as described on the bottom left screen here, you should get out a 0 on the other side. And if you get something that's not 0, that means there's something wrong with your computation. The intermediate results or the final result is wrong. Now, so we have R1CS, but that's not yet what zk-snark takes. zk-snark actually works with something called quadratic arithmetic program. So what they do is we need to first think about these R1CS as individual points. So these are 6-dimensional points. 6-dimensional? Yes, 6-dimensional points because there's 6 of them. And then we use Lagrange interpolation. Essentially, imagine you have a 6-dimensional space of these dots, and then you're trying to weave a polynomial to go through each of them. And in this case, you see, there's on the center of the screen, there's an example of a 2-dimensional space. You have 3 points, and you're using a polynomial to go through all of them. So these are actually encoded polynomials. So how you read this is a coefficient of x to 0, coefficient of x to 1, x to 2, x to 3. So you can actually see that the first line there translates to, so yeah, wait, hold on. Yeah, so it's backwards, right? So it starts with x raised to the third. So you go backwards, it's 0.833 is exponent of x to the third. -5 is exponent of x to the second, and then 9.166 is x raised to the first, and then you have 5 is x to the 0. So if you plug in 1, so again, let's go back to like this graph where you have these points are on 1, 2, 3, and 4 because we have 4 of them. We have 4 expressions. So if you evaluate these polynomials at 1, 2, 3, 4 respectively, you actually do get exactly what we see before. So a quick example I can show is that if you plug in 1 for A1, you would get 0. And if you plug in 1 for A2, you will get 1. And then if you plug in 1 for A3, A4, A5, A6, you would get 0, 0, 0, 0, which is exactly the first line here. Okay. So next, we need to check the polynomial. So because this is no longer just plugging in the values, we're now dealing with polynomials. How do we effectively and efficiently check the correctness of this program execution by evaluating the polynomial? So rather than plugging in the numbers or this 1, 3, 3, 5, 9, 27, 30, and then multiply out the polynomial, it will be a pretty intensive process. What you actually try to do is you take the polynomial and then you try to divide it by this special polynomial, which is z of x, that represents x minus 1 times x minus 2 times x minus 3. What you're supposed to get is some constant h, and then you're not going to get any, if the computation goes correctly, you should not get any remainder. If you have a remainder, that means again, the vector assignment is incorrect. The intuition of this sort of math property is that if you have some function f of x that given input 1 would spit out a 0, that also means that f of x over x minus 1 would give you some number, or not constant, but some like polynomial even, h with no remainders. So essentially, by having z checking essentially the assignment of 1, 2, 3, 4, it's the Lagrange interpolation, like 1, 2, 3, 4, checking that the polynomial evaluates to 0 at all these 4 points. You can sort of do this little hack by just looking at the remainder. And then this is following up on the next slide. This is essentially the steps I'm talking about. You first multiply the polynomials by vector assignments, and eventually you divide by z, and then you have no remainders. That means that the 1, 3, 35, 9, 27, 30 assignment is correct. And at this point, we have sort of proved the correctness of execution. On the prover side, we started with this small piece of code, this expression, this statement, and then we've converted into these 4 constraints. And then, essentially, you fill in the numbers for everything that's in the constraint. And on the verifier side, you started with this statement, and we have converted into this QAP, quadratic arithmetic polynomial. Wait, what's the word? Yeah, program. Quadratic arithmetic program that we can evaluate, and we simply feed in these 6 numbers, and then the verifier is going to say no remainder, and we're all good. But what's missing? It's zero knowledge. Missing zero knowledge, right? No one should see this, right? The verifier shouldn't see this. So how do we do this without getting into too much into the encryption? Because the encryption is actually very hard. We can dedicate 2 lectures on that. So this is almost the same intuition, right? Where we are doing sort of encrypted computation without seeing the clear text of the input. So just like how Brendan used the discrete log property, which is also a trapdoor function, one-way function, where it's easy to compute one way, difficult the other. Here we use elliptical curve cryptography, where one of the key assumptions, similar to discrete log, is this one-way function where if you have 2-point P and Q, and you have P times K, where this times is not your typical times, it's elliptical curve times in a finite field. So this times symbol is not all that accurate. It needs to be specially defined. But you have this P times K equals Q. But given only P and Q, it's really, really hard to find K. Essentially, is that you cannot just do Q divided by P to find K, because it's the division is defined really weirdly. And this is what a typical elliptical curve look like. And to do multiplication, I guess a simple way to explain it is you sort of just jump between points on the curve. Now that's sort of nice, right? You still see a curve, but for elliptical curve cryptography, we actually use finite field elliptical curves, which looks like this. So it's really hard to back out the K if you don't know the K. And so we're essentially using elliptical curve cryptography to encrypt the expression that we had before, A times B minus C equals H times Z. And one thing to note is that because this K value that we have been talking about for the past minute or two is so important and no one should know it, and this is actually a burden to ZK Snark, is because they need to keep this, they need this K, but they also need to keep the secret and no one should know it, which means that it requires a trusted setup step. It's essentially a process to generate this K and then sort of wrap it in a encrypted container. And from now on, you throw out the K and you only use this encrypted K. And if someone knows this K, then your entire ZK system is useless, right? So this is one of the weaknesses. It's because if your procedure is not correct and someone gets to know K, then they can just arbitrarily prove things that and verify would be like, yes, this is correct. So this is the actual verifying steps. This is sort of pretty technical, but I will try my best to explain what each of the points stands for. So essentially, the VK, the first step, it contains the parameters from the initial setup. So I guess like two important things about the VKs. It's encrypted, and so it includes sort of some version of the K that's encrypted. It also summarizes the problem. So as we see, because we are sort of constantly, we started from the original code, and then we turn into polynomial. And then eventually when you're evaluating polynomial, you don't actually need to know the entire polynomial. You only need to know sort of a few relevant parts. So instead of computing the whole polynomial, you actually just need to know these sort of summarized points that's relevant to your calculation. So VK includes all of this. And then, so the second and third steps, it uses elliptical curve pairing, which is, it's the part of the cryptography. It checks for the format of the proof. In particular, it checks for A, which is sort of, A1, A2, A3, A4 is a linear combination of AI, and that A, B, C, the polynomials here, they have the same coefficient. It's not like 1, 3, 35, 1, 2, 35. So that's what it does. And then lastly, for Q4, so for 4, it's very obvious, check for the QAP divisibility. That's what we talked about. If this is true, then we know there's no remainder, and this means that the execution is correct. And because everything's encrypted, so now compared to the previous slides where we have everything in cleartext, this is a way to prove the correct execution, and it does not reveal any sort of secret information. And here, let's do a summary. Essentially, we have here is a process of, start with the argument, and then you turn it into expression, and you turn it into polynomial. Then you use elliptical curve cryptography to prove with encryption that we have that the prover has certain private values that satisfy the problem. Now, this begs the question, or it should prompt us to think, what can ZK-STARK really prove? I think from what you see is that you can prove the knowledge that some set of numbers that satisfy some mathematical format or constraints. And it does require the problem to somehow be translated to QAP. As we've seen, so for mathematical expression like this, there's a pretty straightforward way through R1CS to translate to QAP, which then gets processed by ZK-STARK. But how do you approach something like prove someone is over 21? Anyone? Thoughts? How do you use what we talked about to prove someone's over 21?
Like, don't you ultimately need some kind of like third-party KYC verifier?
Yes, and
like what you could do is like you could have them prove it. They give you a signature of the hash that you can verify and it's sure that, and then you store like the user's wallet and that hash of that signature. Oh no, I'll do this much.
yeah, exactly. So I think Austin made a great point, right? So you cannot prove this outright because being 21 is not a mathematical property. Like you don't live on blockchain and your age is not encoded on blockchain. So you need someone, first of all, somehow translate this arbitrary concept that's your age into a mathematically provable format. And that requires, either a government agency sort of just assigns you, a private key that somehow relates to your age, or you need Oracle, a KYC agent. KYC stands for Know Your Customer. It's like the procedures that banks and financial institutions perform to ensure their customers are legit, not terrorists. So then they provide some sort of mathematical property that's provable on chain. Then you use yours. Then you perform a ZK proof to prove that mathematical property. So
what's the point involved doing all that if you could just prove that you're 21 using like an ID in the first place? It seems like you're proving the proof.
So exactly. So I do want to prompt you to think, right, like whether ZK KYC is necessary, right? It seems like there's a lot of, centralized party. There's a lot of trust already going into it. But think about this. Where did you guys get your ID? The government issues to you, right? So you're already going through that process. But an ID is easily fakeable, right? Like I just make a Like literally, if I copy it and put it on a nice sheet of like plastic paper, like people are probably going to believe it to some extent, like 10, 20% of the bouncer are probably going to let it slide, right? So in that sense, it's not very secure. It's easily duplicatable, right? And the other thing is, if you hand out your ID, that also have your home address on it, right? Who knows that the bouncer is not going to like come to your house and like kill you or something, right? So in that sense, you can with ZK KYC, you can provide just enough information, and you can sort of prevent, you can use cryptography to ensure that no one can duplicate it. So that will be some advantages, but whenever ZK is a really hot topic right now, but I urge you to think after knowing how it works that like, are all the use cases legit? Can they be done in the first place? And whether doing it requires a higher level of trust to some centralized party, which maybe it does, maybe it doesn't, it violates the need for using ZK in the first place. And lastly, I want to sort of bring to your attention to performance considerations. So we see a lot of polynomial computations as we go through the process. And in fact, the number of polynomials, as you see, we started with 4 constraints. It's super linear to the number of constraints. It's actually O of n log n size to the number of constraints. And in turn, because you can like somehow accelerate polynomials by having more polynomials, that means your runtime is n log n. And for example, if you want to solve a ZK Sudoku puzzle, you need 700 of these constraints. You want to verify a SHA-256 hash, which is like, you do that everywhere almost nowadays. You need 20K of these constraints. And Zcash privacy coin requires 500K of these constraints, and the proof speed is about 2 seconds-ish. And Filecoin have, one of their biggest circuit has more than 100 million of these constraints. Just imagine how long it's going to take to prove, right? While this is sort of trivial for certain applications, for Filecoin, like it's probably fine because it doesn't have to be real time. But think about applications such as ZK rollup, where in a sense you're trying to like put blocks together and you need instant or very quick finality, right? Then the proof speed is the bottleneck of having these ZK rollups, ZK EVMs work. And for example, ZK EVM is very, very big, or it has very large constraint size. So lastly, just want to conclude the session with a prover verified demo. I would say personally, I learned ZK, for a year now, and I have never seen it run in a code format. So I'm going to show you, how it actually looks like in code and how it actually works. Just give me 1 sec to switch to this computer. Stop sharing. Cool. All right. So this is sort of the steps that we're going to go through. We're going to start with code, then we're going to compile the code, and then we're going to set up sort of remember we have like set of parameters that we need to generate. And then we need to compute a witness. Essentially, witness is the clear text version of the vector assignment. And then we generate the proof, which is the encrypted version of the witnesses. And then we generate a verifier actually in Solidity. So we deploy that verifier onto a blockchain, and then we interact with the smart contract that is the verifier and have our proof be verified. So let's go to code. I hope this sharing scheme works here. Cool. So the code is pretty simple. We're using this demo file I found on the internet. This language and compiling environment is called Socrates. Apparently, it's like one of the leading and easy to use, like ZK things that you can play with. On the right here, we have sort of this definition of the statement that we're trying to prove. So essentially, this function takes in 2 private inputs, X and Y, and you're computing or you're proving that you know there exists some x and some y, that x times y plus 4 equals 10. Pretty simple, right? Like an example would be 1 and 6. 1 times 6 equals 6 plus 4 equals 10. So you're just proving that you possess this knowledge, but you're not actually sending those two numbers. Cool. Let me see if I still remember how to do this. Yep. So, and just to explain a bit of the setup here. So on the left, we have a virtual machine or a Docker machine that runs Socrates because it requires some complex environment. So I'm just using the Docker file right now. And on the right, we have sort of this local environment that it contains all the files. And these are like local folder is mounted to Socrates so that it has access to it. So the first step we do is to compile this file. So Socrates compile, and it reads the code and it compiles, and it generates a few new files. And then so we already are at the compilation step. So it turns human readable code into machine readable code. And the next step is, as we said, we need to sort of do some parameter generation before we start. And half the parameter goes to the verifier, half the parameters goes to the prover. These are just the enough relevant information that's encrypted that the two parties should know. And this is called setup. We run Docker setup. So it generates, so as you see, right, like VK, so this is verifier key, and it also has PK probably at the beginning, but it essentially generates a bunch of parameters that the verifier and the prover requires to work.
Is that for the elliptic curve kind of?
Yes, this is from the elliptical curve. Yeah, so you see that these are 2 points, like, and pairing is also ECC terminology. Yeah. And then, so we're going to compute a witness. So we know that 106, 203 works here. So we're going to create a clear text version of witness, which is we input 2 and 3. This essentially converts this command line input into a file that the computer can read. It also generates the intermediate results. We'll see. So yes, so we generate this witness, and we can try to see the witness here. So for this very simple code expression, we have sort of 5 including the one that, you know, because of some property is a start you have to include, but you have also 2, 3 as input, private input, and this intermediate result of 6. Yes. So this is what's going to get feed into the program next. Okay, so now we have the witness, we generate a proof. Right, so again, not a surprise, it's going to generate a bunch of elliptical curve numbers, and this is the proof. And we can also see on this side, there should be a proof.json file. So this is our proof, and I'm going to copy this. Yes. And before we, so we set up, and we computed witness, and then we have just generated proof. And next, I'm going to generate a verifier. So Socrates is really nice. Wait, so I need to, okay, I don't remember the code for this. Is this generate verify? Oh no. Oops. Let me see. See, whenever you do a live demo, there's always going to be problems, and I'm not immune here. Let's see. Export verifier, that's it. So export verifier. So you actually do need to export verifier every time you do this, because every time you do setup, it introduces some sorts of randomness such that one setup is different from the next setup. And in turn, because both your verifier and prover uses some kind of parameters from the setup process, so you need to regenerate the generate prover and verifier. So here we have the verifier. And we can see that there's a verifier.sol just generated. It's very old code because this version of Socrates is really, really old. But I try to play with the new version, but then there's a whole lot of dependency issue that I couldn't solve. So here we are using like the version 3 years ago. So you see that this solidity contracts already encodes a lot of the setup information in there. And all you need to do is feed it proof and it'll tell you whether it's good or bad. And what we're going to do here is copy this whole thing, then copy it here. Okay, great. So now we have this verifier contract, and how we run it is essentially we're gonna, well, first we're gonna use truffle to deploy it onto the blockchain, a local blockchain on my computer, and then the test file essentially is going to feed in a proof, which I'm going to copy over, and then if the proof is correct, the test should pass. If the proof fails, the test should fail. So I'm going to copy the proof over. Test files here. Oh, what? Is that right? 2C34. That's not right. Okay, cool. That should work. All right, so we have saved everything. Sorry. And do we have a local blockchain running? We do have local blockchain running. This is the Ganache CLI. And now we just need to run truffle test, I believe. And specifically, I'm going to run this file. So smart contract. Yeah, so truffle test, and then copy the path of this. Okay, let's see if it works. All right, so it's compiling. And it's deploying the contract. And we passed. So that was the correct one. So in fact, with this demo, I cannot even pass in the incorrect values because the witness generator wouldn't allow me. So I can't 100% convince you if I put in the 3 and 4 that it would fail. But just trust me that it works. Yeah, so that is sort of how. Let's go back to the roadmap here. So the proof is now verified, right? So this is also how, and this portion is usually done on the blockchain. So this is sort of a typical use case of zero knowledge proof. You want to some offline non-blockchain computer to do some work, but we're not sure if it would do it correctly, right? Whether it's to execute transactions of the blockchain in a rollup setting, or maybe do some very compute-intensive tasks like video rendering, like data analysis, whatever. But eventually, you want to have it verified and have it settled on public trust blockchain, because that's what we're all about. So then you take that proof of essentially representing the work that's done offline, where compute is cheap, and you bring it onto the blockchain, and then you run the verifier and make sure it's verified. And once it's verified, right, that record is on chain now, right? And then you can say to everyone, like, I did this compute workload correctly, and perhaps you can claim some reward by doing that. Okay, I think I am done on my side, so compute. Yeah, that's the end of the presentation. And we'll have some resources that we'll send later. These are pretty nice. First one is if you look up awesome ZK, it has like 200 links that you can look into. And the second one is talks about like how you can execute a scheme where you prove someone is 21 years old. And exactly what you said, it requires a lot of centralization. Any questions?
Yes.
Could you just repeat why we had to generate the verifier at the very end?
Yeah, so
It's like, oh, during the setup, like wasn't the verifier already kind of generated?
the setup actually
It only generates the key or like the
so it generates some information that the prover have to use and some information that the verifier need to use, right? Because prover is like, it's usually you're usually trying to prove something, right? So there isn't an explicit step of generating a prover. So it's just done by the Socrates code. But verifier is usually something you can deploy onto the blockchain. So it then generates the Solidity code that you can deploy on blockchain. And then you can like send it over to verify. So sort of there's the offline, prover land where compute is cheap. And then there's the on blockchain verifier land where compute is expensive, but proving is relatively easy. And essentially you're able to do a small amount of work, but this work represents all that work that you did offline.
Great. So yeah, again, this entire session is recorded. We'll be emailing out the recording link in our next newsletter. If you guys have any questions, you guys review.